This is the second part of second session of this lecture. I just showed the measurement setup of this sensing. Actually, this is setup used to measure the duty ratio to output transfer function of offline flyback converter. This is a flyback converter, and this is it has this kind of configuration, and we are comparing the AC component of this and this and this and this is the same figure, and this is the equipment impedance analyzer. But it has the wideband. What was that? Wideband frequency tracking gain phase analyzer is here, and this scope watching this measurement. If I can show this the waveforms of the duty ratio modulation, something like that. Unfortunately, there is no screen, no image here, but it would be better if I show this the modulation of duty ratio. Okay, and this one, and I prepared one video for this, but this is a very simple case, and I prepared the video for the loop gain measurement. Loop gain measurement requires some variation. It's not straightforward like this, but so I'll show you the video at that time when we are talking about the loop gain. So you should wait until the loop gain discussion is coming up. Okay, and this is the measurement example. This is an example. This is a buck converter, right? So this is set up. So duty ratio is set up at this point, and switching frequency, and the same configuration. This is the sampling, this one, and comparing later on. We are measuring this, and they go together. And this guy is removing DC and tracking, the extracting the sinusoidal component, even though it has some lousy contamination like this switching the switching frequency noise spike. It successfully catch only this AC component at this frequency. This is measurement. This looks like what? Second order low pass filter characteristics. It has some DC gain, and it has some peaking, and it has some slope, right? Why it has this low pass filter characteristics? Why is that? There is a low pass filter. This is low pass filter. Okay? So this is low pass filter. That characteristic is somehow appearing here, even though you modulate this, still this characteristic is remaining there. Okay? So that's one reason why I emphasized the knowledge fundamentals about the linear invariant system is important here. Okay? So assume this is generated from the low pass filter, then it has 0 dB, not 0 dB, DC gain. So this has some DC gain. And this will be double pole. Omega naught is given by this square root LC, so with some value. And the Q of this, we have this Q. Okay, Q is this R times R. There is a C and L. Okay, this number, I calculate this using these numbers. It is 0.25. So 20 log Q is 20 log 2.5 is larger than 6 dB. But you are not seeing that much peaking here. Let me draw this again. This should be horizontal. Oh boy, this is strange. So very small peaking here, okay? And this slope, if you calculate this slope, this is a -2. So this is -2 slope somewhere here, and the -2 slope is changed to -1 slope somewhere here. So -2 slope, -1 slope, that means there is what? There is 0. omega g is here. So phase start from the 0, and with this double pole, it goes down, and the final phase is minus 90 degree. It will go minus 90 degree, something like this, okay? So if you see this, so you may figure out this, and this. If you know all the story, this frequency response of a linear time invariant system extended to the PWM converter, then you understand this, okay? Without that knowledge, you're just seeing this, but you cannot interpret this, okay? Another important thing is why this 20 log Q is more than 6 dB, but it is very small, okay? This is a measurement. This is a hardware measurement. So in hardware, there are many parasitic resistance not incorporated in the analytical, theoretical prediction. In theory, we just considered this and this, but there are other resistance components here. So damping Q is smaller than prediction. So maybe the theoretical prediction will be like this. Then measurement should be smaller than this always, right? Because you cannot consider all the parasitic components. And if this Q is real one, then phase change should be more upward. So with that high Q, phase is changing, should change something like this. But in this theoretical work, the phase is changing gradually because we have smaller Q in here. In theory, no. In theory, but in hardware, it will be different. Okay, this is this is a theory. So theoretically, it should have this peak, and the phase should have upward to change. But in hardware, you have some parasitic resistance unaccounted in this analysis. So with that, the more damping is provided, then this will be reduced, and the phase change should be gradual than the expected one, right? So understand this, okay? And implication of this. So now you have this, and maybe you understand this in part, not fully, okay? The interpretation of this will come later, and maybe in next section, we'll discuss all the details about that implication of frequency response. What is the real meaning of the frequency response in PWM converter case? Okay, that is in some way similar to the linear time invariant system, but there is some difference. So you should understand that. Okay. Look at this. This is the general cases of the frequency response of our interest, right? So of course we want to have frequency response duty ratio to output voltage that is critical for the controller design, because we are sampling out voltage and process with some feedback controller, and we are changing duty ratio. So transfer function from here to there is very important, very critical for the controller design. And we may want to know the transfer function from here to there. This determines noise characteristic of this. If this is large, then there is some noise AC component. This DC is usually derived from the AC with the rectification. So it has this 120 Hertz noise and some distortion and some spike. Then noise should be removed through this. And you want to have a clean output. So you want to know the transfer function from there, okay? And the impact of this control design on that transfer function is of your important concern, okay? So you want to know the frequency response from here to there. For that, you are injecting this. This is AC signal injection without disturbing the bias point, okay? The AC is appearing here. So this is the DC plus AC. This is ideal transformer now. But you can use any transformer in practice or something else. That measurement technique is very important in practice. Okay, you should measure this eventually. All right. And this is what? This is I/O is perturbation in output current. Okay, usually this load will be changed. The load will be changed in step fashion, stepwise change, or some other noise. So this change in the load register is represented as disturbance in the output current, load current. The same thing. Okay, so we need some source, current source, which represents change in the load current due to this variation of output resistor. So we want to measure ratio between this and this. This is called, it has name. What is that? There's output impedance. Okay, so everything has output impedance. When you are making this PWM converter, you want to make something very close to the ideal voltage amplifier, voltage source. So output impedance or output resistance of voltage source is what? 0. Okay? 0. So you want to minimize this as low as possible. So you want to know this. Okay? So from here to there is important. This is input-output noise rejection ratio. And from here to there is what? This is output resistance, output impedance. Okay? And the relationship between this is open loop, and relationship of closed loop transfer functions from here to there is strongly affected the control loop design. Okay, so the prior knowledge for the controller design is 3 things basically, 3 things alone. Okay, you don't need any more, right? So this is input-output frequency response. So you have transfer function and replace S with J omega. Then you have frequency response. And the condition for this is VP S and IOS as 0. Okay? Because this is when you have this AC, this small signal relationship, this is considered as a linear system. So there is a superposition principle. So when you are evaluating one thing, source of the other thing should be considered as 0. Same is true. This is a dual ratio to output frequency response. This is a load current to output frequency. So there are only 3 important transfer functions in PWM converter. Maybe some other cases, some other system, many transfer functions can be defined, but we don't need that transfer function. The functionality of power supply is very simple. Okay, so this should be known for the control design. This should be known for the input to output, input noise to output noise transfer function. This should be known to evaluate the output impedance, which indicate the goodness of this converter as an ideal voltage source. Right? Only 3. You don't have to consider anymore. Okay, so what we have discussed so far is empirical method. You are not using any small signal model, or you are not using any circuit analysis. You are just measuring this. Okay, as I said in the beginning of this semester, I'll explain the frequency response of PWM converter and the performance of PWM converter, and along with this kind of concept, empirical evaluation, and I'll explain the meaning of that, why that is important. Then I'll give you the knowledge about how to obtain the small signal model which carries the same information you obtained in this empirical method. Understand this? Okay. So this is usually the order is opposite. Most book and all of my previous book, I explained the small signal modeling first, then explain this. But somehow, I thought changing this is much better for the student. Okay. Now, if we go through this, then you have clear idea what small signal modeling is. Okay. Otherwise, when you are learning the small signal modeling, you really cannot understand the meaning of the small signal and the small signal modeling. Eventually, you know everything, but it takes long time and some trial and error type error. Okay, so I'll provide you direct and fast way of elevating your intellectual level on this power electronics. So there are two empirical methods. Empirical means not theoretical, not analytical, just doing some experience. One is using impedance analyzer, and this is the function of impedance analyzer. It inject input sinusoid and sweeping the perturbation frequency, and for at each point, not continuously point, but each, anyway, very short distance between two measuring points, and extract the output sinusoid and compare it with the input sinusoid and generate magnitude and phase curve using the FFT and something else using the DSP chip. Okay, this is the new modern approach. Okay, everything is digital inside the equipment. As I said previously, all of them was done in analog way. Okay. Okay, so this is the function of impedance analyzer. This is experimental method, and the other one is computational method using a circuit simulator like PSpice and Flex something, many other MATLAB and so on. Okay, that is the duplication, emulation of this impedance analyzer, this equipment using software simulator. What they are doing is they perform this time domain simulation as I explained here in this manner. Okay, they perform this measurement using simulation. So this way, the software should first find the equilibrium point, bias point first. So they should reach steady state, and at the steady state, they change this frequency and generate data and decode it, and later on plot them and show on the screen. Okay, so circuit simulator performs a series of time domain simulation to get steady state and sweep the perturbation frequency and the result, process the result to generate the magnitude and phase plot. Previously, this kind of software was not available, maybe 20 years ago, something like that. Right? This was impossible. And writing this kind of code, this computational procedure algorithm, was the topic of the PhD degree. Okay, I was in Virginia Tech, and they have done some internal program, and they tried very hard to develop this automatic procedure, but the commercial product come out first. Okay, so that project is dead because already the industry people, they commercialize this, and one of them is PSIM. This is cheap but dirty, cheap and dirty. Okay, but this is also a good one for the educational purpose, but for the professional use, this has some limitation. And the simplest is very good one. Maybe some other better one will come later. Okay, so now you are doing this with this, and it literally replaces this experimental work. But you should confirm this experiment at least once for one point. Okay, you can use this for your research, and in the final form of your dissertation or whatever paper, you should use this. Okay, so there is a technique of doing this, and Middlebrook, he made great contribution on this, measuring the loop gain of any feedback system in operational condition. Okay, that is not tricky. Okay, to think about it. Right, but he divided this, and he made many contributions. All right, so this is end of section 3.2. Okay, so now you know the frequency response of converter, PWM converter. Okay, here, as I said in the previous section, we used the empirical method. experimental method and the computational method without any theory or without any analysis. And here we are talking about the modeling. Okay, the modeling is a big job, so it comes later. And assume we developed the model somehow. Okay, later on you will learn the modeling process. Here we just take the result and making use of it. Okay, to understand the implication of frequency response in PWM converters. Okay, actually this is the introductory slide, lecture slide for the modeling, small signal modeling of PWM converter. I took 2 pages to introduce the concept of this, right? This is the schematic, simplified schematic diagram of PWM converter. This power stage can be anything, any PWM converter, buck boost or buck boost and whatever converter. And this is PWM. So we are talking about PWM converter. So there is a PWM block. And this is the voltage feedback circuit. We went through this. Voltage feedback compensation, 3-pole-2-0 circuit or 2-pole-1-0 circuit. And 1-pole-0-0 circuit, something like that. All right? But nobody is using the next one. Okay? So we have 3 functional blocks. Okay? And when modeling this, we separate our job. So first, derive a small signal model of this, and derive a small signal model of this. Then this one is easy. This is already linear circuit. So deriving this is very extremely simple. You already know this. This is the non-inverting amplifier. Then gain is G2 divided by G1 and minus sign in front of that. You already know this. So you don't pay attention on this. And first we do this. Okay? All right. So I'll show the final form of power stage model. Okay? The derivation is coming later. Right. And this one is challenging. Okay? Because this modeling was challenging in the past. Now it looks very easy job. The reason for that is many people suffered from that, and they developed the theory, established the theory. Because there is a theory, maybe you take granted for that, but many people suffered from that, right? There are many trial and error method, and one guy go direction, wrong direction, and he go back, something like that. Okay. There are 2 challenges. One is time variance in power stage configuration or power stage dynamics, right? So this is time varying system. So structure is varying all the time, periodically. That is the big problem in the past. They cannot apply any technique. But there are some technique, those type of system, but result is extremely complicated and does not provide any meaningful insight which can be used for design. That was the problem. Discrete time system, some garbage, okay? Pile of garbages is useless, okay? And another one is there is a non-linearity. This is the big non-linearity, typical non-linearity. Input of this is what? Analog signal, okay? Output of this is digital signal, right? Relationship between this and this is very complicated. They call it the describing function method or something like that, right? Very complicated analysis has done in the past 20 years ago, and they found the simple way of doing that, okay? So this too was the barrier, and the purpose of the PWM modeling is also important. So what is the modeling? What do you think hearing the term modeling? Modeling is changing the original things in another form for your purpose. Okay? I don't know if this is correct. For the semiconductor people, for the MOSFET, they have derived the circuit model, complicated circuit model. In the PSPICE, they have very complicated model. Okay? That can be considered as a model. The purpose of that is very clear. They want to represent the physics of the semiconductor using the circuit component. That was their model, their purpose model. If you have a very complicated system and you want to have the simple model, then you ignore all the unimportant details and just keep the main frame of their dynamics as a simplified model. Okay, so different modeling has different purpose, and the purpose of our modeling of PWM converter is very simple and very definite. We want to use all the techniques you learned using the linear time invariant system to analyze and design and to understand the dynamics and control of PWM converter. Okay, so you want to use the existing knowledge you already know, assume you already know all the knowledge of transfer function, Laplace transformation, Bode plot, root locus, Nyquist 등등, and so on. And you want to use those knowledge directly to the PWM converter. Then PWM converter should be modified in some sense. Okay, that is the modeling, and that is our purpose of the modeling. Okay, if you come up with the final model of PWM converter, you treat them as a linear time invariant system, and you use all the existing knowledge you learned from your undergrad, and that is our purpose modeling. Okay, I wrote down here. We want to use the terms and the format that have been used for the linear time invariance, in particular the frequency response concept. Okay, so by deriving the model, we directly apply the frequency response concept to the PWM converter, because the frequency response provides all the information, all the steady state and the dynamic information of the linear time invariant system. You want to do similar things to the PWM converter, but there is a big assumption there. The steady state operating point is not changing or changing very narrowly. If we change widely, it's impossible. But if it remains in the close neighborhood of that point, this is a very good approximation. And all of the story we'll be talking about this is equally applicable to the linear time invariant system, or all the techniques developed for the linear time invariant system can be applied to the PWM converters if we use proper small signal model of that on the assumption. So first assumption is there is a small variation in the operating point, and the other one is small signal assumption. AC component is much smaller than DC component. Okay, that assumption is also used in electronics when you are deriving the small signal model of BJT amplifier. You are not thinking about the BJT itself. You are using the circuit, equivalent circuit, pi model, T model, something like that. It's the same concept is here. Okay. All right. Okay, maybe this is enough for the introduction of the modeling, and please understand the procedure I'm teaching. Okay, later on you will learn the modeling. Okay, then the gap will be disappeared between this one. All right. Okay. Thank you for your attention.